In this video, we're going to be talking about solving logarithmic and exponential equations. And of course, we have to remember how to turn a log into an exponential equation and vice versa, when a has to be greater than 0 and a can't be 1. All right, so let's work through our first example. So I'm going to be asked to solve for x here, where 2 log base 5 of x is equal to log base 5 of 9. The first thing that allows me to manipulate and move this thing around is that I have the same base for my logarithm, which is 5. So knowing what I know of log rules, I know that this 2 is going to actually be here, so if I rewrite it, I get log base 5 of x squared equals log base 5 of 9. So because I have the same log with the same base, it's almost as if those two things cancel out, and I get x squared equals 9. If I take the square root of both sides, I get x is equal to positive 3 and x is equal to negative 3. But before I assume that both of those things work, I have to actually plug them back into my original to make sure that they do verify my x values. So looking at this problem, I know that whatever this x is has to be greater than 0. And if I plug in a positive 3, that checks out. But if I plug in a negative 3, that doesn't make it greater than 0. So I have to reject this answer. So the only thing that works is x equals positive 3. And I can actually verify this graphically. If you were plugging this into your graphing calculator, I'd set two equations, y equals this side and another one for y equals this side of the equation, and see where their point of intersection or points of intersection will be. So if I solve this algebraically, I get positive 3 and negative 3, and I'm looking for where these two sides will meet each other graphically. So the blue line and the red line cross in only one point, and that's going to be x equals 3, which verifies what we found here. So now let's take a look at another logarithmic equation that we're going to be solving for x. So x appears in two places now. So because I have the same base, log base 5, on the left-hand side, that allows me to combine these two things using log rules. So I write it like this. Now keep in mind, when I have the result of addition, that comes from multiplication. So when I condense this into one log base 5, I get log base 5 quantity of x plus 6 times the quantity of x plus 2 equals 1. So I'm going to use my handy dandy arrow trick here to get rid of my log expression. So I get 5 to the first is equal to x plus 6 times x plus 2. If I work that all out, I'm going to end up with x equals negative 7 and x equals negative 1 because this is a quadratic. Now, just like in the last problem, I have to check whether or not negative 7 and negative 1 will work. So I can do that algebraically, and I can plug that back into these two things, knowing that x has to be greater than, or this whole thing and this whole thing has to be greater than 0. So when I plug in negative 7 here and here, that actually doesn't work. But when I plug in negative 1 to both of these, it actually checks out. And if I wanted to do this graphically, I would set up the left side of the equation as 1 y equals, and then also then graph y equals 1 to see where the intersection point will be, or if it will have the 2 that I'm looking for. So I would be looking for negative 7 and negative 1. And just like last problem, it only had one point of intersection, which is actually going to be at negative 1, comma 1. So that justifies our x equals negative 1 solution right there. So now looking at this example where we're given an exponential equation asked to solve for x, where x is the exponent of 2 to the x equals 5, I know already that the x is going to give me some number value because 2 to some number gives me 5. It's not going to be a pretty one, but let's apply our log rule here. So I'm going to rewrite this as log base 2 of 5 equals x. And again, it proves that some number x is going to satisfy this here. So what I'm going to do is use my change of base. So log of 5 over log of 2, and x is approximately 2.322 using my graphing calculator. And I can also prove this using graphing utility, where I set one side of the y equals to 2 to the x and the other one equal to y equals 5, and I find my point of intersection, which will give me the nice rounded answer of x is approximately 2.322. Let's take a look at one more exponential equation. So I have 4 to the x minus 2 to the x minus 12 equals 0. That kind of reminds me of a quadratic equation. We're going to bring that back in just a moment. But I have my exponentials, or my x's, as exponents here, which if I just had one, I know what to do with that, but now it's in two places. They don't have the same base. What am I to do? Let me show you. So the first thing that I hope that you see to do is that this 4 to the x and 2 to the x have a relationship among the bases. So I'm going to rewrite 4 to the x as 2 to the squared, or 2 to the 2, to the x minus 2 to the x, right? Same deal, minus 12 equals 0. So what I have here is that these almost look the same as that. I'm going to swap them because I know that if I were to bring 2 to the power of x and x to the power of 2, they both give me 2x. So swapping this doesn't change anything. It's just a way to rewrite it. And the reason I do that is because now I have 2 to the x and 2 to the x. So they're comparable. Now, I can keep working with 2 to the x, and you are welcome to do that if you want to, but it's kind of confusing to me to keep writing powers to powers. So a math trick that I like to employ here is I'm going to let some variable, I'm going to choose y, doesn't matter, equal to 2 to the x. So I'm going to rewrite that in terms of y here. So 2 to the x is really like y squared, and this is like 2 to the x to the power of 1, so minus y minus 12 equals 0. See where I was going with that quadratic thing? So now I'm going to factor it, and I get y minus 4 and y plus 3. So if I set them equal to 0, I get y minus 4 equals 0, and I know that y is like 2 to the x minus 4 equals 0. So that's 2 to the x equals 4. And if I do the same thing for this guy, I'm going to get 2 to the x plus 3 equals 0. 2 to the x equals negative 3. So now I have to do a little bit of thinking here. And that is, this x is going to be 2 because 2 to the power of 2 is 4. And then I look here, and there's no power of x that's going to give me a negative 3. That's going to satisfy these two things up here. So this doesn't even work. So my algebraic answer is x equals 2. And if I wanted to show that graphically, just like the other three problems that we've looked at, I will graph the left side of the equation and the right side of the equation, and I find the intersecting point at 2, 0. So x equals 2. And that's going to do it for this video.